All right, so now what we're going to do is we're going to take this drawing of Lewis structures to the next step. And we're going to draw the Lewis structure for a particular ion. This ion right here is the polyatomic cation, ammonium. Ammonium has an overall +1 charge. How many valence electrons does ammonium bring in? Well, nitrogen is going to bring in 5 valence electrons. Each one of the hydrogens is going to bring in a total of 4 valence electrons. So we're looking at 9 valence electrons. But how does this positive charge impact our total number of valence electrons? Well, it impacts it by that positive charge means we subtract one of the total number of valence electrons. So our valence electrons for ammonium is 8. And so when we draw ammonium, we need to draw it like this. Our central atom is nitrogen. We have hydrogens all around. This right here shows all of our 8 electrons have been drawn. Now what we need to do with that, though, is we need to kind of emphasize that this is one whole unit and it has a positive charge. So that right there is the appropriate Lewis structure for the polyatomic cation, ammonium. Cyanide, Cn-. Well, how many valence electrons does this bring in? Well, each one of the carbon is going to bring in 4, the nitrogen is going to bring in 5, so we're looking at 9 valence electrons again, but what makes this a little bit different is this has a negative charge. So what does that mean? That negative charge means that we add an electron. So to draw this structure, well, Cn, we go through the exact same process. The only difference is, what we're going to do is we're going to end up with a triple bond between the carbon and the nitrogen. We're going to bracket this. Make sure that you know that that is a pair of electrons rather than like an I or something like that. That has an overall -1 charge. That is the structure. That is the structure of the polyatomic anion cyanide. All right. Now, the next step in all of this is to look at what are known as formal charges. So formal charges are basically when you look at something like ammonium, or when you look at a molecule, you say, okay, well, that whole thing has a positive charge, but is that positive charge like assigned to one particular element within that molecule? So in some Lewis structures, in some examples of molecules, there are multiple Lewis structures that are going to obey the octet rule, but you'll be able to determine which one is the actual best representation for that molecule. So if we took, for example, CO2, we could draw CO2 in 2 different ways. Now I'm kind of skipping some of the steps here, and I'll come back to them, but that's one fair model of carbon dioxide. This is also an acceptable model of carbon dioxide. And so to kind of send that message home, there are 2 electrons, 4 electrons, 6, 8, 10, 12, 14, 16. So 16 electrons are drawn. Well, carbon's bringing in 4, and each oxygen's bringing in 6, so that's 12. So this is a molecule with 16 electrons. Okay, so now let's look at our next model. Well, that's 2, 4, 6, 8, 10, 12, 14, 16. Again, 16 electrons have been drawn. So between these 2 representations, they're both acceptable in the sense that they both have 16 electrons drawn. So they've met some of our rules. But what we want to do is we want to dissect that a little bit more. And we want to figure out, is one representation for this better than the other? And so we use formal charge to do that. So the formal charge is calculated to determine which Lewis structure is most reasonable or best. Generally choose the Lewis structure in which the atoms bear formal charges closest to 0. So you want basically every single atom to have no charge whatsoever. That's your ideal situation. Generally choose the Lewis structure in which any negative charges reside on the more electronegative element. So think about that Pauling scale of electronegativity where fluorine was the most electronegative element because that can take on that negative charge, whereas something that's less electronegative, well, doesn't really want that negative charge quite as much. Now, how do you actually calculate the formal charge? Your formal charge is calculated by Well, two different ways. One of which is your formal charge is equal to your valence electron number minus the unshared electrons of an atom minus half of the bonding electrons. Okay? Or you could use valence electrons minus unshared electrons of an atom minus number of bonds attached to an atom. Okay, so both equations are going to work. Now my personal preference is to use this lower model or this lower example where we're looking at our valence electrons minus unshared minus number of bonds. Now we're going to do some practice problems. We want to look at our two different structures. For carbon dioxide. We got that guy. And then we've got this guy over here. There we go. Okay, so these are two different models for carbon dioxide. Now, our aim is to get our formal charges, so charges on each one of those atoms, to be 0 or as close as possible. And so what we want to do is we want to look at the, let's look at this oxygen right here. And then we'll look at this carbon right here. The good thing is that whenever I look at the formal charge calculation for this oxygen, because that oxygen is identical to this oxygen, I'm going to get the formal charge for that oxygen at the same time. Okay, so let's start it out with, what was this equation? The equation was to look at the valence electrons. I'm going to write as val minus, and I'm going to put these in parentheses, minus my unshared electrons, and that's unshared electrons, not unshared pairs. And then finally, I'm going to subtract number of bonds. Now, as I said, this is my personal preference. So if you choose to do it the other method, that's going to work just fine for you. I'm going to go ahead and erase that, and I'll come back to that in just a little bit. Okay, so how many valence electrons does oxygen bring in? 6. How many unshared electrons is this atom, does this atom have? Well, it's got 1, 2, 3, 4. 4 minus how many bonds? That's 1 bond, that's 2 bonds. Okay, that's not a double bond, that is 2 separate bonds, so count that as 2 bonds. So 6 minus 4 minus 2 is going to be 0. So my formal charge for this oxygen is 0. My formal charge for the other oxygen is also 0. Okay, now let's go through, what's our formal charge for this carbon? Again, the same formula. Valence electrons, bringing in 4. Unshared electrons, 0. And number of bonds, 1, 2, 3, 4. So 4 minus 0 minus 4 equals 0. Okay, so this molecule, I tried to say model and molecule in one word. This molecule, or this representation of this molecule, is what I'm looking for. This shows a formal charge on every single atom of 0. Okay, so now what I need to do that's a little bit different for this other model is I need to label my oxygens because of the fact that one oxygen has a triple bond and one oxygen has a single bond. Okay, so what I'm going to do is I'm going to label them oxygen A and B. And I'm going to do my calculation for A right here. So how many valence electrons does oxygen bring in? Still 6. How many unshared electrons does oxygen A have? Well, it's got 2. Then, how many bonds does it have? Well, it has a triple bond, so 3 bonds. So 6 minus 2 minus 3 is going to be equal to positive 1. So this has a positive charge on it. It's important to make that distinction that it is a positive versus a negative or something like that. Okay, so now let's look at oxygen B. Well, again, we're using, I'm going to highlight this formula right here. I'm using that exact formula again. Well, how many valence electrons does oxygen bring in? It's bringing in 6. For this oxygen that I've labeled B, how many unshared electrons does it have? 1, 2, 3, 4, 5, 6. It has 6. And then, How many bonds does that oxygen have? It's got 1. So the charge for this is -1. Okay, so now I'm looking at a CO2 molecule with a positive charge on one end and a negative charge on the other end. What I want to do, just for, completion's sake, is let's talk about this carbon. This carbon has a triple bond on one side, a double bond, or a single bond on the other side. So carbon's bringing in 4 valence electrons. How many unshared electrons does this carbon have? 0. And how many bonds does it have? Well, it's a grand total of 4. So that has a charge of 0. Okay, so now what we're doing is we're looking at 2 different molecules. One of them, this guy right here on the right hand, on this side of the screen, that is the correct structure, because what we have is every single element with a formal charge of 0. The opposite, where we've got our triple bond, well, that's a decent entry because the net formal charge for that molecule is 0, but we've got a positive end and we've got a negative end. So basically, if you can land at a representation for a molecule that has no formal charge whatsoever, especially, and no formal charge on any one of the elements within that molecule, then that's exactly what you're looking for. So we've got that summed up with the formal charges are all 0 and the overall charge is also 0. All right, well, I hope this was helpful, and this does take quite a bit of practice. I'll post a practice worksheet that you can go through. But anyway, I think this is fun. Formal charges, Lewis structures, everything like that. All right, well, have a great afternoon.